Let's begin with a quick review of Newton's third law, which states that for every action, there is an equal and opposite reaction. This principle is central to understanding the interaction of forces between objects. We will explore examples to see how this law applies in real-life situations. Consider this key idea. The same force exerted on a small mass produces greater acceleration than when exerted on a larger mass. Let's explore this with the example of a cannon and a cannonball. The cannonball experiences a much greater acceleration than the cannon because of its smaller mass. The forces exerted on both the cannon and the cannonball are equal in magnitude. However, due to the difference in mass, the acceleration of the cannonball is significantly higher based on Newton's second law, F equal to ma. This principle underlines how Newton's third law operates across systems with unequal masses. Let's move to another example. A tennis ball and racket interact with equal force as per Newton's third law. However, the tennis ball undergoes greater acceleration due to its smaller mass compared to the racket. This demonstrates how forces result in different outcomes based on mass. Next, we have an example of two blocks, X and Y, moving on a smooth surface. Block X exerts a force on block Y and vice versa. This interaction produces acceleration of 1 meter per second square for both blocks. The mass of block X is 6 kg and is 1/3 of the mass of block Y. Thus, the mass of block Y is 3 times the mass of block X, which is 6 kg times 3, equivalent to 18 kg. We are to determine A, the magnitude of the force exerted on block Y by block X, and B, the magnitude of the force F. Let's analyze the forces involved step by step. In this slide, we are drawing the free body diagrams FBD of the individual blocks X and Y. Notice that we focus only on the horizontal forces, excluding the vertical forces, which are the normal force and weight. Both blocks experience the same acceleration of 1 meter per second square as they are being pushed together by the force F. When block X pushes block Y, it exerts a normal force Fyx on block Y. This is the action force as described by Newton's third law. For block X, there are two forces acting on it: the applied force F and the reaction force Fxy, which is the normal force exerted by block Y on block X. According to Newton's third law, the action force Fyx that acts on block Y is equal in magnitude but opposite in direction to the reaction force Fxy that acts on block X. This demonstrates the action-reaction force pair between the two blocks. To determine part A, first we consider block Y. The force exerted on block Y by block X, denoted as Fyx, results in a net acceleration. Using resultant force is equal to ma, we calculate Fyx, which is equal to 18 kg multiply 1 meter per second square, we have 18 newtons. In the first method, to find the applied force F, we consider block X. The resultant force on X is applied force F minus Fxy is equal to the mass of block X times the acceleration, which is 6 kg times 1 meter per second square, giving us 6 Newton. So F is equal to 6 plus Fxy. From Newton's third law, Fxy is equal to Fyx, and we know that Fxy is equal to 18 Newton from part A answer. Thus, the applied force F is equal to 6 plus 18 equal to 24 Newton. In the second method, we analyze the motion by treating the two blocks X and Y as a combined block's body as the system. This approach simplifies the problem by focusing only on the resultant external forces acting on the system as a whole. Since Fyx, the action force exerted on block Y by block X, is equal to Fxy, the reaction force exerted on block X by block Y, are internal forces acting on the same system. They cancel each other out according to Newton's third law. This leaves us with only the horizontal applied force F, which is also the resultant force, acting externally on the combined system. Using Newton's second law, F is equal to mx plus my multiplied by A, and substituting the given values, mx equal to 6 kg, my equal to 18 kg, and A equal to 1 meter per second square, the resultant force is F equal to 24 Newton. This calculation demonstrates that the combined system accelerates due to the external force F, with internal forces balancing each other out. Let's summarize the key takeaways. First, we review Newton's third law. We then examine the characteristics of action-reaction force pairs and study several examples to solidify our understanding. We also clarify that certain force pairs, like normal force and weight, are not action-reaction pair. In conclusion, Newton's third law helps us understand the interplay of forces in diverse situations. By analyzing examples, we have seen how force and mass determine acceleration and how action-reaction forces manifest in real-world systems. Thank you for your attention.